Hello friends, this is part 4 of 2022 paper C-6 Thermal Physics BSc 3rd SEM Dibrugarh University. So we have already solved from question number 1 to question number 4. So now I'm going to give you the answers to the questions or question number 5A and B. So now let's start. Before we start, please do subscribe the channel, also hit the bell icon and like the video. Okay. So here is the question number 5A, using Maxwell's thermodynamic relation so that Cp minus Cv is equal to R. So first let us prove this equation. Okay. So now you see specific heat at constant pressure is given by the specific heat. The specific heat at constant pressure is what is that? Cp represents specific heat at constant pressure, which represents del Q by del T, which at constant pressure. Okay, so this is the del Q is the heat and del T is the temperature, change in temperature. Okay, and also it can be written, this is temperature T and del S is the entropy, okay, by del T. So T, right? Del S means change in entropy, this is change in temperature. Okay, and because del Q, this change in this heat supply, that's gonna be equal to T dot del S, right? So now, and same thing at constant volume, just wait, let me copy this. Okay, so at constant volume specific heat is given by, just let me write, at constant volume, okay, it is given by Cv is equal to del Q by del T at constant volume is equal to T into again del S by del T at constant volume, right? So now if the entropy S is regarded as a function of T, and V, since this ds is perfectly perfect differential, is a perfect differential, so we can write ds is equal to del S by del T at constant volume V dt plus del S by del V at constant volume T dV. We can write this. Okay, now you see what we can do here. Just give me 1 second. If this is the case, then what we can do, just let me copy this last step and let me go to the next slide. So here you see this is the last step we have got. So therefore what we can do here, so first let us obtain this. So del S by del T at constant pressure, that can be written as del S by del T at constant volume, and here we have dt. So I have written now del S by del T, so that's why here we're gonna write del T by del T, this is at constant pressure, plus, and del S by del V we have here. So as we have written here del T, so here it can be written as del V by del T. So this is T del V by del T. So here it is constant pressure. So that's why if we multiply both sides by temperature, capital T, then this equation, this above equation will be this, right? We're gonna get this. Okay, now from the Maxwell's second relation, thermodynamic relation, we're gonna get del S by here we're gonna write, since del S by del V at constant temperature is equal to del P by del V at constant, sorry, not V, that's supposed to be T, okay, at constant volume. This is Maxwell's thermodynamic relation. Maxwell's thermodynamic relation. So that's why what we can do here. Now you see here we can replace this del S by del P by this term. So if we do so, then what we can have, we can have this, just let me copy this above step and let me write here. Okay, so just give me a second. Just wait, just give me a second. Okay, here you see, sorry, here we can replace this term. Okay, so if we do so, then what we're gonna have, we're gonna put this one here. So then that is del P by del T at constant volume. That's what we have got, right? Now you see, this implies now you say this is going to be equal to 1, so we can keep this one like this, right? So hope you have understood this. Now yeah, just wait, let me replace this one. Okay, now you see, let me copy this last step and let me go to the next slide. Okay, now from this what we can do, just we can bring this term to the left hand side of the equal sign, then this equation becomes this, right? So hope you have understood this. Now you see what are these two terms. So here you see, let me go back to the first slide. Yes, so let it be equation number 1, let it be equation number 2. So these two terms can be written as Cp and Cv. So using 2 and 1 and 2, we can write this Cp, and this is constant at constant pressure, this is at constant volume. So Cp minus Cv, that's going to be equal to this. So let me copy this and let me paste here. That's what we have got, right? And for a perfect guess, so what we get, PV is equal to RT for 1 mole of gas. So if that is the case, so what we can write here, okay, right? So here at constant volume, if you take the volume as constant, so what we can get here, if you differentiate dP by dt, del P by del T, that's going to be equal to R in case of constant volume, right? In case of constant volume, this V is taken as constant. So right, so that's why we can write this is equal to R by V, right? Del P by del T. And if you take that pressure is constant, then its derivative gonna be del V by del T at constant pressure, then P should be regarded as constant. So here del T by del T, that's gonna be 1. So here we're gonna get R. So that's why this implies this, right? That's what these two imply. Okay, now let us use these two results now let us use these two results here. Okay, if we do that, so let me copy these things and let me go to a next let me take a new slide. Here is the new slide, you can see. So therefore what are you gonna get? CP minus CB, and let me do one more thing. So I forgot to mention here using 1 and 2, using 1 and equation number 2. So CP minus CB, so here what we're gonna have, T R by V actually. Okay, so one more thing I have missed, I think that is what, okay, no, that's fine. Okay, so what we're gonna have here, here R by V and again R by P, that's what we're gonna have. Okay, so now you see T R square P into V, PV is again RT, so let's put here. So then CP minus CB, that's gonna be RT R square. Here we're gonna have RT, so TT cancels and R cancels R square, so that's gonna give you CP minus CB is equal to R. So this is the required relations, right? So that's how we can prove. So let's move on to the next question. So our next question is discuss the results of Andrew's experiment. Okay, so now let me show you the answer. So answer to 5B. So here is the Andrew's experiment, not completed yet. Let me go to the next page, pause the video and note these things or take the screenshot. So this is the page number 2, second page. Okay, so not completed yet. And this is the page number 3. Okay, so here you see, so you have to start from here, page number 1, this is 2, and this is the last page. So answer is completed here. So now let's move on to next question. So what is the here you see question number 5B, or this question, derive Boyle's temperature from van der Waals equation. So let me give you the answer to this question as well. So 5B, or, so here is the 5B answer. So you start from here, this is for page number 1, and here it is 2, second page, take the screenshot. Okay, and this is the third page, last page. Okay, so the paper is completed now. So do subscribe to the channel and do like this video and share with your friends. Thank you for watching. See you in the next video. Best of luck.